We will answer 4 questions in today's video. The first of that being, how do we derive a 3D heat diffusion equation for heat generation using Cartesian coordinates? Well, I want you to remember one main concept, one that seems very simple but can help us a lot for this derivation, and that's going to be our conservation of energy. Conservation of energy is our energy in minus our energy out plus our energy generated generation, and that's going to be equal to our energy accumulated. So that's going to be our main concept for this question. And from that, we want to imagine a 3D object in order to derive our equation. That'll help us simplify how we're going to get there. Let's use a cube. And a cube has 3 dimensions, of course. Pretend these sides are all equivalent and that I'm not that bad at drawing it. And those 3 dimensions are our dz direction, our dy direction, and our dx direction. If we draw that in a 2D field, we have our z direction, or positive d direction is what I'll call it, our positive y direction, and our positive x direction. If we show that on the cube, we have x dx, or change in dx, or our change in x, our y direction, our change in y, and our z direction, and our change in z direction. So how do we get from here to the 3D heat diffusion equation for heat generation? Good question. Well, you want to remember that we're trying to find the energy accumulated. And our energy accumulated is going to be equal to our temperature, because it's the heat diffusion rate. It's a change in temperature multiplied by our heat capacity, multiplied by the density in order to get rid of the kilograms in heat capacity over our change in time. You always have to remember there's going to be a change in time because we're thinking about time. And because it's a 3D object, you want to have it multiplied by the volume. That's going to be dx, dy, dz, because it's a 3D object, right? If you have a 3D object, you're multiplying it by 3 dimensions in order to get that volume. You're also going to have your energy generated. So for your energy generated, that's going to be your heat flow multiplied by your rate of heat flow multiplied by your volume once again, because you're looking for that in the volume. So how are we going to find the energy in minus the energy out? There's a lot of directions that are going on. Well, what we can do is we can use a Taylor series expansion in order to derive the equation for the energy in minus the energy out. We have our dx direction and our dy direction. Oh, frick. We have our change in x, and our x. How are we going to use the Taylor series expansion in order to find that? Funny thing is, Taylor series is very helpful. So if we visualize that, we have our function. This is for Taylor series. And for Taylor series, we know that our position x, there is a slope. We know the slope of the function. So the change of the function at x. And in order to find our x naught, our change in x, we can assume our x naught is equal to x, and that is how we're going to find our dx. So let's apply this back to our, and now if we write that out as an equation, we get that our function at dx is pretty equivalent, I would say, to our function at x plus our change in the function over the change in distance at x naught is equal to x multiplied by our x naught minus x. Applying that back to our change in x and our x with regards to heat flow, we get that our heat flow at dx, because that's what we're looking for, is relatively equivalent to our heat flow at x plus our change in heat flow over our change in x at dx is equal to x at our change in x minus x. And so that is directly taken from our Taylor series expansion. So now how do we find the energy in minus the energy out? I mean, we have the heat flow, but how do we get that? Well, we can consider our energy in minus our energy out as our net heat flow. And so our net heat flow is equivalent to our heat flow in, so our heat flow at x, minus our heat flow out, which is our heat flow at dx. And guess what we just found? Our heat flow at dx. For this equation, we assume that we know or we can find the heat flow at x in order to solve it. So if we plug this equation that we just derived in, we can find that some units are able to be canceled. So our heat flow at x can be canceled out, and then all we get is our slope. So our change in heat flow over change in distance at dx is equivalent to x at dx. Simplifying that to something even more visually appealing, we get our slope is multiplied by dx. And this is for our heat flow for x. Well, we have 3 different dimensions. So how are we going to find the heat flow at all 3 of these dimensions for our heat flow in minus our heat flow out for conservation of energy equation? Great question. You can do the exact same problem that we just did and simply apply z and y. All you have to do are essentially change the x to a z or a y, and that gets you exact same equation. And so I will write that out. So our net heat flow at x is equivalent to our change in heat flow at x over our change in distance at x multiplied by our change in x. For y, it's the exact same equation, substituting y in for x, and it's derived the exact same way. I'm just not going to do it for consistency's. I'm just not going to do it because it's a long process and there's not a necessary reason to, because I already did it. So our net heat flow at C is our heat flow at C over change in C multiplied by the change in C. Now we have all 3 parts of our conservation of energy equation. We have our energy accumulated, our energy generated, and our energy in minus our energy out. Let's put this into a larger equation that we can then simplify in order to more easily use it. Drawing that out, we get our energy accumulation equals our energy in minus our energy out plus generation. And our energy accumulated is our density multiplied by our heat capacity multiplied by our temperature over our change in time multiplied by our volume. Dx, dy, dz. Our energy in minus our energy out is each one of these equations added together, because you have 3 different directions that the cube is going in, because it's a 3-dimensional object, so 3 dimensions, of course. So and I completely forgot to add a negative to this. So remember, there's a negative in front of all 3 of these equations, right? You see here, since you're subtracting your dx, you have to change all of these signs to negative if there's not a negative and a positive instead. So we have our change in heat flow at x over our change in x multiplied by our change in x plus our change in heat flow at y over our change in y multiplied by our change in y plus our, and again, these are all negative, plus our negative change in heat flow at z over our change in z multiplied by our change in z. And then we're going to add our heat, our energy generated, our heat generated, which is going to be our heat flow multiplied by the volume once again. In order to simplify this equation even more, we can use Fourier's law. Now, Fourier's law states that our heat flow is equivalent to negative thermal conductivity multiplied by our area multiplied by our change in temperature over, that does not look like a T, our change in temperature over our change in distance. So if we were to find the heat flow at X, we would have the same thermal conductivity, or just a thermal conductivity, multiplied by an area, which in this case would be our dy multiplied by our dz as seen on the cube, because if you're finding X, you have your dy and your dz, multiplied by our change in temperature over our change in distance, which is X in this case. And apply that to your heat flow at, once again, apply that to your heat flow at, now apply that to your heat flow at your position Y and your position Z, and you get the exact same equation, just replacing your area with whatever units are not right here. So for your dy, you have dz multiplied by your change in x, by your change in time over your change in y, and then for your heat flow at z, you have your change in y multiplied by your change in x multiplied by your change in temperature over your change in z. We can substitute these three heat flow equations for x, y, and z back into each of our net heat flow equations for x, y, and z. And that will simplify our final 3D heat diffusivity equation down to this little number, which is actually bigger than our original. Yeah. Negative d over change in x multiplied by our negative thermal conductivity times change in y, change in z multiplied by our change in temperature, or change in x multiplied by d, or change in x. And I'm going to skip over just so you don't have to wait through this entire equation. Here is our almost completed final equation. We're going to want to simplify just a little bit more. As you see here, in each one of these equations, or each one of these, as you see here, in each part of this equation, we have dx multiplied by dy multiplied by dz. Right here are dy, dz, dx on the outside, still multiplied. Once again, in this equation, once more, and our final part of the equation, our generated energy, we have dx multiplied by dy multiplied by dz, or our volume. So we can cancel this out and get a much smaller equation. Additionally, we can factor out our thermal conductivity as well as divide our density and our heat capacity over to the other side in order to get our change in temperature over our change in time, which is essentially our 3D heat diffusivity final solution. What you'll notice is that this part of the equation, our thermal conductivity over our density and our heat capacity, is equivalent to our thermal diffusivity. And so our final simplified equation can be written as our 3D heat diffusivity is equivalent to our thermal diffusivity multiplied by our energy in minus our energy out through all dimensions plus our energy generated, which is our heat flow over our density multiplied by our heat capacity. So the summation of this problem is essentially we looked at the conservation of energy for a 3D object, in this case a cube. We found all the dimensions, our dc, dy, dx, applied Taylor series expansion in order to figure out how we can understand how to get our energy in minus our energy out, as well as used common knowledge in order to find our energy generated and our energy accumulation. Use that to create a conservation of energy equation and then simplified it in order to find our 3D heat diffusivity equation for heat generation using Cartesian coordinates. Now that we've determined our 3D heat diffusion equation for heat generation using Cartesian coordinates, we can apply that to a one-dimensional heat diffusion problem. Let's take our heat diffusion equation, and since it's only in one dimension, we only need to use one dimension. For this, we'll be using our d squared t over dx squared and forget about the rest of that volume. So we'll write this equation so we have general knowledge over here. Our change in temperature over our change in time is equivalent to our thermal diffusivity multiplied by the second derivative of temperature over the second derivative of the distance traveled plus our rate of heat flow over our density and our heat capacity. And that's just a general equation that we want to remember for this entire problem. So let's say that we have a slab, and on one side of the slab, there's insulation. The slab is of length L, and there's obviously heat flow through it, and there's air traveling up on one side. That air we'll say is 20 degrees on the outside, and the slab is 80 degrees Celsius. Our heat is flowing out of this volume. Our X is right here, and where x equals 0, and x equals L at this other end, and in this direction we'll say is positive. So let's use Fourier's law and apply Fourier's law to this concept. Fourier's law, in this case, will be negative heat flow since it's flowing in the negative x direction, and that's going to be equivalent to our negative thermal conductivity multiplied by our area multiplied by the change in temperature over the change in position. Now you want to remember there's a cross-sectional area, A, and so it's our negative heat flow at the length multiplied by the cross-sectional area, and that is equivalent to our thermal conductivity multiplied by our area multiplied by the change in temperature over the change in distance. What this equation is telling us is that the heat loss will be equivalent to the heat generated within our slab. Now, if you think about the temperature profile, it will create this curve and end in a straight line where the slab is insulated. We know this from a previous video where we explained how we can gain this temperature profile by learning about how the heat flows through the slab. Going more in depth, you'll see at this length, the slope is increasing, and that is because our length and our area are larger. It's going across a larger length and cross-sectional area. So if that's increasing, then our slope also has to increase to remain equivalent with the heat loss. And as it levels out, our length multiplied by our cross-sectional area becomes smaller, so our slope becomes smaller. And the reason that those two values, or those three values, are changing is because the thermal conductivity in this cross-sectional area do not change, as well as the heat flow. The heat flow remains constant within the slab. And so this is how you derive an equation to show the profile, the temperature profile of a one-dimensional heat diffusion problem for heat generation with an insulated side. So now what if we want to find the equation for a 2D heat diffusion with no heat generation? That's a great question. We can use our equation from our 3D heat diffusion and transform that into something that we can use for a 2D heat diffusion equation with no heat generation. The first thing I want to start by doing is visualizing the problem. You're going to want to create a grid to visualize that two-dimensional heat diffusion because you're going to have two dimensions, our x and our y direction. And those x and y directions, we can split this grid into 4 columns and 4 rows, right? Not perfectly even, but good enough. And we'll say that this is the positive x direction. And so going from left to right is our positive x direction. And going down to up is our positive y direction. You can put temperatures on either side of this grid to help visualize this problem as well. So we'll just say that on the right side of our grid is 100 degrees Celsius, our left side is 200 degrees Celsius, above the grid is 310 degrees Celsius, and below the grid is 250 degrees Celsius. We're not really going to do anything with those temperatures right now, we're simply deriving the equation, but it's a nice way to visualize how the heat might diffuse across the grid. Next step, we're going to take our three-dimensional heat diffusion equation and transform that into something that we can use for our two-dimensional heat diffusion problem. Shrink that down so we can better see it. And we recognize that there is no heat generation, right, for this problem. So that's going to be equivalent to 0. Additionally, there are only two dimensions, our x and our y direction, so our z direction is going to be equivalent to 0. And then our rate of temperature, our change in temperature over our change in time is also going to be equivalent to 0. So that equation that we're going to use is 0 equals our thermal diffusivity multiplied by our two dimensions, the second derivative of temperature over our second derivative of the change in x plus our second derivative of temperature over our second derivative of change in position, y. Now, to understand this problem even further and derive that equation, I like to just put that our 0 is still dt over dt, our change in temperature over our change in time. But once again, remember that that is equal to 0. That's a very important concept to know for later for deriving this equation. And that's equal to our thermal diffusivity, our second derivative of temperature over our second derivative of our position of x, our second derivative of temperature over our second derivative of our position y. So now that we know that, let's look back at our grid. And we'll say that for this square, for every square really, this is a change in x, right? You've moved over in our x direction, so that's going to be a change in x. And if we look at the left side of this square, that's going to be a change in our y direction, right? You're going from one position of y up, so it's going to change our y direction. And our time, we also have to consider. So our time is equal to some time n multiplied by our change in time. Our position x is equivalent to, we'll use a variable I that's commonly used for our x position, multiplied by our change in x. And our y is equivalent to j, again, that's commonly used as a variable to denote a y multiplied by our change in y. Using these elements, we can say that the temperature in this square of the grid, we'll just use this square. Let's say we want to find the temperature at this square in the grid. That temperature is going to be ij. You're at a position I and at a position j, right? You have your x and your y dimensions. So that's your temperature T at I and j. If you go over 1, So let's say you're going to the left. You're going to subtract from your I direction because you're decreasing in your X direction. If you go to the right, you'll increase by 1 in your X direction, and your J direction will stay, or your J will stay the same because you're not increasing or decreasing in your Y direction. But if you were to go up 1, you would increase your J because you're increasing in your Y direction, and going down 1 would decrease your J. But again, once again, you're not changing in your X direction, so your X is going to stay the same, which means that your I is going to stay the same. And this goes for the entire length of the grid, this concept. So over here would be ti plus 2, and so on for above and below. Applying that concept and putting it towards our equation, you'll find that the change in temperature at your position T of Ij over time is equivalent to our temperature at Ij, position Ij, at time n plus 1 minus our temperature at position Ij at our time n, which is before n plus 1, of course, over our change in time. That is equivalent to this expression right here. And that is equal to our thermal diffusivity multiplied by the second derivative temperature, which in our x position, that's going to be our temperature at I plus 1, right? Because you're changing your position for this part of the expression. You're changing your position, so you want to add to your I. Your j is going to stay the same because you're not changing in your y direction. That's going to come later. And your time is going to remain constant, so it's just going to be n for the entirety of this part of the equation, minus your temperature at your position I, j, the position you're trying to find the temperature at, over your change in position. That is going to be minus, because this is a second derivative of temperature, you're going to do this twice, your temperature at the position you want to find at the same time, subtracted from your position 1 over for x, over, at the same time, over your change in x, your change in position x. And because this is the second derivative for your change in your position x, you're going to once again divide by your change in x. Now you want to add this to the second derivative of temperature over your change in position y second derivative. So that's going to use the same exact concept here, and you're simply going to apply it to your j and use your change in y instead of your change in x. So your temperature at position I, j plus 1, at the same time n, minus your position at the time you want to, or the temperature you want to determine at that position ij, over your change in y, minus your temperature at the position you want to determine, the time n, minus, and this is at time n too, minus your position at I, j minus 1, at time n, over your change in y. Once again, this is a second derivative for our position, so you'll divide this entire expression by your change in y. We want to simplify this equation down even further, right, to make it more easy to understand. So our change in position of x is equivalent to our change in position of y, which is just equivalent to our change in position. In this expression, right here, as well as this expression, is equal to delta squared, our change in position squared. So now we can take all of these terms and combine them together to create one large expression. So our temperature at our position that we want at time n plus 1 minus the temperature at the position that we want to know at time n divided by our change in time is equivalent to our thermal diffusivity multiplied by our temperature I plus 1 j at time n. And you'll notice that this expression right here shows up 4 times. So you can combine all of these expressions and say that it's minus 4 times our temperature at the position that we want, time n, plus our temperature at I minus 1, Jn, plus our temperature at I, J plus 1, and minus temperature, or plus our temperature at I, J minus 1, n. And that is all divided by our change in position squared, like we said before. Remember that this side of the expression is equivalent to 0, so we can just say that this is 0. Let's divide our thermal diffusivity over as well as multiply our position squared over to get rid of those terms. And so we have 0 is equal to our thermal diffusivity multiplied by, or sorry, that 0 is equivalent to this expression right here. And we want to find the temperature at position ij. So let's add that over to the other side and divide the other side by 4 to get our final expression of T temperature at our position ij at time n is equal to Ti plus 1 j. So we're just rewriting all of this once again. We're reiterating this element, and this element. This. And that is all divided by 4, or 4 right here. So that is how the average temperature for a single cell, the temperature at a position I, J at time n, can be determined using our 3D heat diffusion equation that we derived, and now deriving a 2D heat diffusion equation with no heat generation. So now with the knowledge that we just obtained, let's use that problem and apply it to an Excel spreadsheet. We wrote down some temperatures before for each side of the grid. As you know, that the temperature on the left side of the grid, so T left, that is equivalent to 200 degrees Celsius. Our temperature at the right side is equivalent to 100 degrees Celsius, not 1,000, and our temperature above, so we'll just say T up, is 310, and T down is 250 degrees Celsius. Let's create that grid of temperatures that we had before. On our left side, we have our 200 degrees. Drag that all the way down to however many values you want. Above, we have our 310 degrees. Below, we have our 250 degrees. 250 degrees. And on the right side, we have 100 degrees. Using the equation that we just derived, we know that our temperature in this position of the grid is equivalent to our temperature to the right plus we should also consider that we're going to divide it by 4 eventually, so put that in parentheses. Our temperature to our right added to our temperature to the left, added to the temperature above, added to the temperature below, and divide that entire expression by 4. Now, if we drag this down, you'll find that the Excel spreadsheet does not enjoy this. That's because it's a circular equation. In order to amend this situation, we have to change some settings. So to change that, we're going to do File, go down to Options. It's really far down. Then go to Formulas, Enable Iterative Calculations, increase the maximum iterations just for safekeeping. apply that, and now our equation works. Let's take this and spread it throughout the entire grid. And now we have a fully functional Excel sheet that shows how our temperature diffuses across a grid. And you'll notice that if you look at any part of this grid, the average of the block below, above, to the left, and to the right is equivalent to the temperature in that spot.